Welcome to This Explainer. Today, we're diving deep into the incredible engineering behind the James Webb Space Telescope by contrasting it with its legendary predecessor, the Hubble. We're going to unpack exactly what it takes to build a literal time machine, one capable of looking back 13.5 billion years. To really grasp just how revolutionary Webb's design is, we have to start with this famous quote. Back in 1675, Isaac Newton wrote this to his contemporary, Robert Hooke, and over time, it's basically become the perfect summary of the scientific process itself. Every single new discovery builds upon previous work, and Webb's ability to see the first stars, well, that builds directly upon the foundational discoveries of the Hubble Space Telescope. So here is our roadmap for today. We'll be looking at standing on a giant's shoulders, seeing the invisible infrared, the L2 advantage, engineering the golden mirror, staying cool in deep space, and finally, a new golden age.
Let's jump right into Section 1, Standing on a Giant's Shoulders.
Since 1990, Hubble has absolutely revolutionized our cosmic view from its low Earth orbit, which is just 300 miles up. It confirmed black holes, it measured exoplanet atmospheres, and it even helped discover the accelerating expansion of the universe, which was a Nobel Prize-winning achievement. But Webb was built to go further. Its mission is to peer back over 13.5 billion years to witness the very first stars and galaxies forming right out of the darkness of the early universe. But to pull that off, Webb requires an entirely different kind of vision. That brings us to Section 2, Seeing the Invisible Infrared. Here's the thing. Because the universe has been expanding ever since the Big Bang, light from 13.5 billion years ago physically stretches out as it travels across space to reach us. So those shorter, bluer wavelengths get stretched into longer, redder, and significantly dimmer wavelengths. By the time that ancient light finally reaches Earth, it is shifted completely into the infrared spectrum. And infrared is essentially thermal radiation. It's heat. We can't see it with our naked eyes, but we can definitely feel it. Now, to capture those incredibly faint, red-shifted signals, which, to put it in perspective, is kind of like trying to detect the pulse of a flashlight on the moon all the way from Earth, Webb needs an absolutely massive mirror. It features a 6.5-meter primary mirror, giving it over 6 times the light-collecting area of Hubble's 2.4-meter mirror. This upgrade allows Webb to gather objects up to 100 times fainter than Hubble can see, achieving the exact same resolution in infrared that Hubble gets in visible light. It's truly mind-blowing.
All right, Section 3, Location and the L2 advantage.
Unlike Hubble, which sits safely just above Earth's atmosphere, Webb actually orbits the Sun at the second Lagrange point, or L2. This is a special gravitational sweet spot where the Sun, the Earth, and the Moon are always in the exact same part of the sky from the telescope's perspective. And that's absolutely crucial because it allows Webb to keep its massive protective shields continually blocking those heat sources, keeping its sensitive optics permanently facing out into the freezing, dark cosmos. And this number right here brilliantly illustrates the sheer scale of the mission. Webb operates 1.5 million kilometers away. That is more than 4 times farther from Earth than the Moon. Because of this extreme distance, unlike Hubble, which was specifically designed to fit in the Space Shuttle payload bay for regular astronaut servicing missions, Webb was designed with absolutely zero plans for a rescue mission. It has to work perfectly, flawlessly, completely on its own. Let's move to Section 4, Engineering the Golden Mirror. So, the obvious question is, how on Earth do you fit a giant 6.5-meter mirror inside a rocket? Well, you don't use a single piece of heavy glass like Hubble did. Webb's primary mirror is segmented. It's actually made up of 18 foldable hexagonal segments that were tucked away like a giant piece of origami for launch. Once in space, tiny mechanical motor assemblies called actuators move each segment in 3-dimensional space. They painstakingly align these individual segments in tiny 5-nanometer steps until they achieve a single perfect focal length, acting as one giant continuous optical surface. The materials chosen for these mirrors are an absolute marvel of modern engineering. A solid glass mirror of this size would be way too heavy to launch. So instead, the segments are made of beryllium. This metal was chosen for its extreme lightweight properties and its incredible structural stiffness at ultra-low temperatures. On top of that beryllium is a microscopically thin layer of gold, because gold is highly efficient at bouncing infrared light. And finally, a protective topcoat of amorphous silicon dioxide, which is basically a microscopic layer of glass, protects that delicate gold from the harsh, unforgiving environment of space.
Which brings us to Section 5, Staying Cool in Deep Space.
Remember how we said infrared light is literally heat? Well, that means any warmth coming from the telescope's own electronics would completely wash out those faint signals from the early universe. So we have to ask, how do we keep this massive, power-hungry instrument cold enough to function when it's being constantly bombarded by the sun? Well, the answer is literally chilling. The optical side of Webb must be cool to near absolute zero, hovering right around negative 230 degrees Celsius. Meanwhile, just a few feet away, the sun-facing side of the spacecraft is baking at around 100 degrees Celsius. Maintaining this extreme temperature differential is quite literally life or death for the mission. This staggering temperature gap is achieved through a super clever component called the Deployable Tower Assembly, or DTA. During launch, the whole telescope is squished together. But once it's in space, the DTA extends using telescoping graphite composite carbon fiber tubes. It physically pushes the freezing cold optical elements away from the hot spacecraft bus. It acts exactly like an insulated handle on a hot iron skillet, preventing the heat of the spacecraft from conducting up into the mirrors. And protecting all of this from the sun is a gigantic 5-layer sun shield roughly the size of a tennis court. It's made of a special heat-resistant polyamide film called Captain. Get this, each layer is incredibly thin, just 25 to 50 microns. The unique kite-shaped design, along with the very precise gaps between these layers, creates multiple internal reflections. This setup radiates the sun's intense heat out through the corrugated edges and completely away from the telescope. Let's not forget the smaller details that make the whole shebang possible. To unfold this massive sun shield and position those mirrors, Webb relies on lots of ball bearings and actuators. But normal mechanical liquid lubricants, they would freeze solid instantly in the cold, airless vacuum of space. So Webb relies on a very special dry film lubricant called MOS2 to ensure the booms and latch mechanisms slide perfectly in an environment with zero oxygen, zero humidity, and near absolute zero temperatures. Finally, let's wrap up with Section 6, a new golden age. It's really important to understand that Webb isn't some replacement for Hubble. It's an incredible partner. You see, Hubble was optimized for shorter, ultraviolet, and visible wavelengths of light, which gives us those stunning, colorful pictures of space we all know and love. Webb, on the other hand, is optimized for longer infrared wavelengths. This allows it to literally cut right through the thick cosmic dust and massive clouds of gas that block visible light, revealing the hidden stellar nurseries and distant galaxies hiding behind them. Working together, these two giants cover a massive, complementary spectrum of light. We've got Hubble observing in the visible and ultraviolet, while Webb steps in with its staggering deep infrared vision. Their combined power is ushering in a brand new era of cosmic discovery, giving us a broad, totally unprecedented view of the universe. But honestly, the most exciting part of this entire explainer is realizing that Webb is specifically designed to answer questions we haven't even thought to ask yet. As it peers through cosmic dust and looks back 13.5 billion years to the very dawn of time, it leaves us all with one really profound question. What unknown secrets will we uncover when we finally look back at the very beginning of everything? Thanks for joining me today, and keep looking up.